This is Richie Jarvis for Under British Skies on Astronomy FM, and today I'm talking to Dr. Paul Lynam, who's a resident support astronomer from the University of California's Lick Observatory here on the top of Mount Hamilton. Hi, Paul.
Hi.
Thanks for talking to me today. What is it that you do up here?
So I'm one of three resident staff astronomers on the mountain of Mount Hamilton, just outside of San Jose in California. And Lick Observatory is a very historically significant observatory, one of the first or the first observatory permanently staffed at high elevation. Shortly after it was opened in 1888, it became the property, as part of the deed of trust of James Lick, the founder, it became the property of the University of California, which at that time was located primarily at the Berkeley campus. Since that time, the University of California has expanded into 10 campuses all over the state of California, and we provide observing facilities here at Lick for that community of astronomers primarily, plus 3 national laboratories. So that's the Los Alamos National Laboratory, the Lawrence Livermore National Laboratory, and the Lawrence Berkeley National Laboratory. Lick Observatory is operated under the auspices of the University of California Observatories, which also includes the Keck Observatory on Mauna Kea in Hawaii. Many of our client astronomers will be trained and qualified here at Lick using facilities here prior to graduating and moving on to observing using Keck facilities at Mauna Kea. And many of their pilot programs are done here, and many of their instrument development programs and tests are also executed here prior to moving over to the Big Island of Hawaii.
So you make sure everything works here on the scopes here prior to shifting it over to the big ones?
It's a useful test bed in that sense. It's not mandatory in any way, but it's a very convenient location. The Lick Observatory itself and the University of California Observatories themselves, UCO, are administered from the University of California campus down at Santa Cruz, which is also a relatively convenient location. So there we have a series of maintenance shops where a lot of modern instrumentation gets constructed. Right now, for example, the GPI or GPI instrument is in its final construction phase, which is due to go to the Gemini South telescope down in the Atacama Desert of Chile. So the University of California has quite a lot of resources to throw at astronomical instrument development, new technologies, and also regular programmed observing and graduate student and undergraduate student training. So as a support astronomer here at Lick, I work in concert with 2 other colleagues on a shift-by-shift basis, and also in concert with people supporting us locally, engineers, mechanical engineers, electronic engineers and software engineers, and a support staff down also located at the Santa Cruz campus with a similar and broader knowledge and a greater range of experience to support the operation of both Lick and Keck observatories. My role in that is multifaceted. We have a regular ongoing programme of observing on several of our telescopes on a nightly basis. So in that line of support work, I am involved in providing troubleshooting should problems happen during the night for the visiting astronomers, and remote observers as well. Also introducing visiting astronomers who are unfamiliar with the instrumentation we have here and the operation of a telescope, supporting their experience here at Lick Observatory. Another aspect is the public outreach component, which is ever growing in astronomy now, and certainly for Lick as a historically significant location. And I also conduct my own original research. My original research program is the study of the large-scale structure of the universe, cosmology, observational cosmology. And we are looking primarily for signatures or non-signatures of something similar to, you may have heard of the Great Attractor. So I'm involved in a peculiar velocity survey which looks at clusters of galaxies all over the sky to measure their individual motions and determine the motion of our own Milky Way galaxy with respect to the reference frame that the average motion of that collection of clusters of galaxies reveals. What you can then do is compare the motion of the Milky Way with respect to the reference frame from these clusters of galaxies with an additional comparison motion which we determine from the cosmic microwave background radiation. if, as we believe, or as we hope, the universe is homogeneous and isotropic on the larger scales, those two motions of the Milky Way, with respect to those two separate reference frames, should theoretically co-align. One of the founding faiths or principles of modern cosmology or cosmological ideas is something called the cosmological principle. And the idea is that if you look on the largest enough scales, the universe should appear the same in every direction. So it should be isotropic, it should look the same in every direction. And we hope that all the material on the larger scales and all the laws of physics and so on should be equivalent and operate equivalently at every point within the universe. So the behaviour and content of the universe on the largest scales should be uniform or homogeneous.
Physics should behave in exactly the same way here on Earth as well as out in the cosmos as well.
Now, on the smaller scales, like where we are on Earth, if you look out the window, we're in a room right now, if you look out the window, we can see that that is not the case because the scale is too small. We're here, we can see constructions and features here that are not the same or uniform to what we see outside, because if we look outside the window from where we are now, we're looking down over the hill into the city of San Jose. If we step away from the Earth, then we start to see largely void space, but we see a few planets and concentrations of matter. So again, that scale is not large enough for us to see this homogeneous and isotropic behaviour in the universe that we expect to find. So we have to really go to very, very large scales. We see structures, galaxies and so on, which is still not large enough scale. And then we even go to clusters of galaxies, and we still see these concentrations of matter in the universe separated by large expanses of space or voids.
Oh, so you're actually trying to find the point in the universe where everything just looks completely flat and bland.
That's exactly true. That's exactly the point. We're looking for the scale in the universe at which everything looks uniform and the same no matter what direction you look. But we now know from our research up until this point that we have to go to very large scales because we still see structures. And even we go to the cosmic foam, and we now think that maybe the cosmic foam is the fundamental view of the universe on the larger scales that we have. Cosmic foam is a popular term to describe how we view the universe on the larger scales. When we do our surveys using redshift maps and so on, we measure the position and velocity of the individual galaxies and clusters of galaxies, and then we have to neglect the gravitational effects that bind individual galaxies in clusters and so on. And on the larger scales, we think the universe looks something like the inside of a sponge or something, which consists of chains and walls and nodes of galaxies, and the nodes are where the galaxy clusters lie, where these chains and walls intersect. And they define large regions that we call voids. So on the largest scales, or the popular idea is that this cosmic foam is how the universe looks, and it's going to be the same in virtually every direction. And the laws and the behaviour of the universe would be similar on those large scales. However, there have been recent, since early 1970s and so on, there have been a succession of surveys performed looking at this largest scale structure using various different tracer particles in the gravitational field of the universe. Some have used spiral galaxies in clusters, some have used bright cluster galaxies, giant elliptical galaxies that we know tend to live in the centres of clusters of galaxies. And we have used those to measure the velocities in all directions around the sky. What these different surveys have created is some sense of confusion at some level, that when you look on these large scales using different traces in the gravitational field, the average motion that you detect with respect to those reference frames that you construct tends to vary. So they're not consistent no matter how large the scale you go. And we're always limited by the telescopes we have and the instrumentation that we have. We struggle to get to the largest attainable scales to see these motions, this average bulk motion, hopefully coincide with the bulk motion that we detect on the larger scales, which is with respect to the microwave background radiation. So to summarise, the background radiation is what we believe to be the leftover remnant from the birth of the universe, the hot Big Bang. And when we look at the microwave background radiation with a satellite or earthbound detectors in the right wavelength regime, one of the first signals that we see, of course we see these famous ripples in the cosmos, which indicate an imprint of structure that we think evolved over the history of the universe to create some of the large-scale structure we see now, like clusters of galaxies and superclusters. But the dominant signal on top of that is what we call a dipole, a hot and cold point over an all-sky map. And we believe that this hot and cold dipole results from the motion of the Milky Way with respect to this cooling recombination era following the hot Big Bang. If you look at the W map, you'll typically see the all-sky survey, and what, depending on the rendition of the data that you look at, the popular and significant data that W map is trying to find is this small scale variation across the whole of the map. The renditions that I commonly see have a largely green or turquoise mottled appearance, and it's these small deviations that WMAP is deliberately set out to see, and that derives from an earlier satellite called COBE, where this was first determined. So there are three significant things in the data. First of all, that there is this very, very overall uniform temperature, which is what is referred to as a black body, or almost a perfect gas, which tells you almost the optimal temperature or the current temperature of the cooling universe at the time the universe changed its phase. And that was a very, very significant result with COBE in the 1980s. It was almost a perfect black body spectrum. We call that a black body, a perfect cooling gas. But on top of that, COBE detected these very small 1 part in 10,000 variations in temperature, which gave support to the inflationary addition to the standard Big Bang cosmology. And the idea being that these small deviations in temperature that we see at COBE, at the point where the universe reionized, were the seeds on which structures could condense, and around those condensed structures gravity could develop over the history of the universe, over the Hubble time, and the gravitational effect could force more and more material to condense into those peaks or troughs of the density distribution in the universe. And we believe that these minuscule variations in temperature are the seeds on which modern day structure in the universe was formed, our galaxies, our clusters and so on. Had there been no seeds in this inflationary epoch, had the temperature and the nature of the universe been perfectly uniform without these minuscule variations, we probably wouldn't be here, because the density fluctuations wouldn't have evolved, and the universe would be perfectly smooth perhaps, and every particle would be separate, equally distant from every other particle, so nothing would have combined. So these seeds that were seen by COBE and then later also confirmed and developed upon by WMAP are very important to our understanding of the universe. However, on top of the largest, most dominant signal, on top of all of those that is largely removed from the WMAP data as an initial step, but is also very important, is something called this hot and cold dipole, which is a Doppler effect, we believe. So we are surrounded by this, on a large scale, this hot thermal imprint from the reionization of the universe, but the Milky Way is moving through space. And there's a Doppler effect that we see as we move in one particular direction, the direction the Milky Way moves towards. When you look at the reference frame of the cosmic microwave background radiation, has a hot, slightly hotter pole or hotter point, and behind us in the opposite direction we have a slightly cooler point.
Based on the fact that the Milky Way is just moving through through this radiation that we're picking up. This is how it's interpreted. It's very important to say it's interpreted this way. I mean, it's not confirmed, but this is how we interpret it. It's a Doppler effect, and it's the largest signal that must be removed before you start seeing small variations. Right. Yeah. But you can use that as a way to determine some kind of reference point, right? A reference frame that you can then use a different set of astronomical objects, be they clusters of galaxies or galaxies, to compare against. So if we then for a moment ignore the cosmic microwave background dipole, and we choose a different set of astronomical sources. So for this argument we'll choose clusters of galaxies all around us, and we then measure the motion of our Milky Way with respect to those clusters of galaxies all around us.
if the universe is going to be uniform, behave the same, and there's going to be no weird gravitational effects going on the largest scales, on the largest scale you can survey using that technique, you would expect that the motion you recover for the Milky Way galaxy with respect to your clusters of galaxies or astronomical reference points would align perfectly with the motion that you've detected with respect to the cosmic microwave background radiation.
That makes sense, yeah.
So the curiosity in all of this is that when you actually perform that experiment using various different astronomical sources, you do not find that to be the case. And this is incredibly perplexing for cosmologists in general. One of the early signatures, one of the early evidence of these things was something called the Great Attractor in the mid to late 80s, where these two vectors, we call them a vector, so you have a vector for the corresponding to the motion of the Milky Way with respect to the cosmic microwave background, and then you have a second vector with corresponding to your reference frame, whatever that may be. In the 1980s, this experiment was performed, and something called the Great Attractor was posited, because the vector with respect to our motion was towards the Virgo cluster of galaxies and beyond, or the Perseus-Pisces direction, revealed that there appeared to be a large gravitational concentration that was pulling our vector away from alignment with the cosmic microwave background. And this has been constantly reinvestigated, and the surveys have got ever more sophisticated, using ever more data and new techniques, always in the hope that we're going to put this thing to bed and finally at some scale these vectors will align. But the more we do it, the more the vectors seem to misalign with the reference vector of the cosmic microwave background, and indeed they misalign with each other as well.
Oh, really?
Depending on the technique used. So there is really something revealing in the sense that we can't explain yet, that we can't justify or support with these type of experiments that the universe is homogeneous and isotropic on the scales that we are probing, and there may be signatures and features and behaviours inherent to the tracing particles that we're using in these gravity fields that may be sending us down blind alleys. For example, if we use a cluster of galaxies as our tracing particle, do we use spiral galaxies in those clusters? Do we use the giant galaxies in the middle? Do we use a collection of elliptical galaxies more typical of the constituents? How do we know they're real clusters of galaxies and not line of sight chance alignments of overdensity of galaxies just because of where we happen to be looking? And over time we refine these techniques. So addressing those particular queries, we can use X-ray satellites to identify clusters of galaxies quite clearly, because clusters of galaxies, bona fide clusters of galaxies, will actually shine in X-ray light, and they're not point sources, they're diffuse gas, so we can use certain techniques to identify bona fide clusters, and then we can use basically a standard candle technique, the brightness of these galaxies at certain distances within these clusters that we know are bona fide galaxies, to help us indicate their distance by measuring the brightness, and then we have to assume something about their intrinsic brightness that will give us some measure of their distance to us, and we can then do a redshift measurement which has a velocity component. So we have a distance by velocity and a distance by redshift. We can subtract the two distances, and the only residual is purely velocity. We average that all over the sky, and then we take the average measurement and we recover this vector with respect to R.
So when are you expecting to see some result? I mean, you must be taking data all the time, and you're finding that these vectors are different across the sky. So are there any theories about, okay, what's going on?
This is the curious thing. So these surveys have gone on using many different techniques, and each time a survey comes out, it seems to be the case that they're not consistent.
Yeah.
So many astronomers will then move on to something where they feel they can achieve more, or they will pursue it. So my original investigation started as a collaboration between British astronomers in Liverpool and German astronomers using the Rosat satellite in Germany, in Munich, and we sought to improve the sample. We sought to clean our sample to avoid these line of sight projection effects, to identify bona fide clusters using the X-ray data. And then we went and resurveyed the sky, and we found that the signal was reduced, but also statistically, because you start to have less objects in your survey, the uncertainty started to grow.
Yes.
So we could with confidence say that we were able to eliminate certain galaxies and identify certain features, and maybe suggest that the galaxies that we were using in particular were not the optimal representative galaxies that should have been used for those kind of surveys. So then you move on from that and you start to select other candidate galaxies or representative galaxies in the clusters, where you can select groups of them within the same cluster to average out your statistics and improve your statistics. And you can also try and improve your observational techniques. When this originally started, we were doing this using visual data, using the Charge Couple device, CCD cameras, at a range of telescopes all around the world. This was a global survey. At the time, the cameras available to us with the large enough format so we could see our target galaxy, plus get a very, very accurate measurement of the background sky around it. We could only use these optical detectors. Ideally, at that time, we would have wanted to use the infrared regime, because our uncertainty in the infrared regime is much lower and our statistics are much more improved. Because largely the galaxy light from a typical elliptical galaxy is dominated and smoothed out by massive stars, and the infrared gives you a much more representative measure of its brightness. The infrared is also much less affected by obscuration effects of dust in our own galaxy and the galaxy you're studying. So that removes some of the uncertainty in your measurement. But at the time we commenced this, the large format infrared detectors were not available. But now they are. So we're moving forward to continue our investigations and hopefully reduce our error bars on our measurements, performing our survey in the infrared regime, and trying to understand the behaviour of our galaxies in the meantime. Individually interesting objects as well, where we're finding, if we study them and we find their characteristics somewhat unusual, we find that they have perhaps multiple nuclei inside them, which are revealing about the evolution of the galaxies. How did they form? Giant elliptical galaxies with multiple nuclei seem to indicate either they form by mergers, or they may form by cannibalising their cohabitees within the cluster of galaxies that they occupy. So this is all moving forward, and we're contributing to the debate and the confusion of these vectors. But it's still a tantalising challenge to see how far we can get and what scales we need to survey to actually get our measurements to align with our cosmic microwave background radiation measurement. And certainly, as I said at the outset of this discussion, our interpretation is only an interpretation that the dipole of the cosmic microwave background is a Doppler effect. There could be other explanations to be explored about that.
It's very nice to find another Brit over here in California, up here at the Lick Observatory. So, do you live up here?
Yes, so I'm a relatively new arrival here at the observatory, and I'm resident here on the mountain. It's about 1 hour away from civilization in San Jose, down a very, as I'm sure you've seen, down these 365 narrow curves with names like the end of the world and oh my and crocodile jaw, which are reflective of the approach to the observatory. But I arrived here in May of 2011, after I had worked for some time down in South America in Chile. I had worked for the European Southern Observatory there for 6.5 years as an astronomer at the Paranal Observatory, operating the Very Large Telescope. Prior to that, I had been working in Munich, or on the periphery of Munich, at the headquarters of that organisation. And prior to that, I had been working with my collaborator at the Max Planck Institute in Germany. So I originally did my PhD in Liverpool in the UK, and prior to that I had done a master's degree at the University of Kent, and prior to that I had done my undergraduate degree at the University of Central Lancashire. And this is all following a childhood interest in astronomy, dating back from when I had one particular event in my childhood that turned me onto astronomy for the rest of my life. And I was got very interested very quickly and went through the local astronomical society, who guided me in my teens and youth and kept me on the straight and narrow. And I was looking at astronomy lectures rather than smashing up telephone boxes during my childhood in Leicester.
Excellent. What's next for you? Are you planning to stay here for the next few years while you carry on working on this project?
I'm one of these people I actually enjoy very much. There are many different types of astronomer. Some are very much motivated by using high computer power and being able to have the universe on their desk, basically some theoretical astronomers and cosmologists particularly. Mm-hmm. And there is a centre of excellence for that in Durham, for example, in the UK. Mm-hmm. There are other astronomers who enjoy the concepts of astronomy and they enjoy hammering through their data or studying one individual object ad infinitum. And there are other astronomers who will be fascinated by the technology or the environments, the extreme environments. But I'm interested in operating and working with telescopes. Mm-hmm. And that also gives you the opportunity to travel, certainly, to these places. I'm an observer more than a theoretician. And more than an observer, I quite enjoy supporting the operations and being present at the cutting edge of astronomy. I mean, my particular research field is interesting to me, but it's a very narrow field, as you've probably determined from this conversation, and quite challenging, and there's only a few people in the world who will be working on that. However, the opportunity that being a support astronomer at an observatory has is that you're exposed to all of the modern astronomy and all the modern research projects that are ongoing at that observatory. And if you go to a large or versatile or a dynamic observatory, there's lots and lots of things to stimulate your interest. So your knowledge of astronomy becomes very broad. And you also develop skills in supporting technology, and you see the evolution of these things. And their observatories, as I'm sure you'll appreciate and your listeners will appreciate, are very special, unique places. They're almost monastic, but they are a very special environment to work in, and I find that very stimulating.
Coming up the mountain to look, I mean, it's an absolutely fascinating facility you've got here. You've got the old telescopes, you've got the new equipment as well. So
you have 9 enclosures and 10 telescopes. And they all range in vintage. So we have the original 36-inch great refractor, which is the mausoleum to James Lick, the founder, the wealthy California millionaire who left his money to many good causes, the largest of which being this observatory, the construction of this.
And he's buried underneath there.
He's interred in the pedestal of the telescope. He's interred in a pillar.
Yeah.
And you can visit my boss at some point, I'm sure. And then we have a 1 metre or 40-inch telescope that we're sitting in the control room of right now, which is at the other end of the building, the northern end of the main building of Lick Observatory. And that's used on a nightly basis and deployed for multifarious research projects, both postgraduate and undergraduate projects, and training and public outreach nights. Then we have...
So the public can, if you're in the area, you can actually come up here at night and in the summer, I believe, and use the...
Yes, unfortunately they're not ad hoc drop-in centres, but you can certainly take part in ticketed events. We have what was called a Summer Visitors programme and a Music of the Spheres. So the Summer Visitors programme is every other Friday night throughout the summer here in California, where you can come up for a few dollars and look through the 2 telescopes. We put an eyepiece on the research telescope. And then we have the Music of the Spheres on the Saturday nights, which is a concert series. And again, after the concert, the musical recital, we open the telescope enclosures up to viewing. And we also provide a lecture on the history of the observatory on those nights. And we invite one of the prominent California astronomers to give a lecture on their research topic as well. So moving on, then we have the 40-inch telescope, or the nickel telescope that we're sitting in the control room of right now. We have James Lick's Great Refractor. We also have a very interesting, historically significant telescope, which you see the enclosure of just below us. That's called the Crossley telescope, which is the result of 2 things that don't normally go together, which is toilets and carpets, because that telescope was originally built for Andrew Ainslie Common in the UK and was deployed just outside London. It was then Andrew Ainslie Common made his money in toilets, sanitary ware, and shortly after it was relocated to Halifax in Yorkshire to Edward Crossley of Crossley Carpets, and who was also, I believe, in the Houses of Parliament for some time. And then Edward Crossley realised, after the horse had bolted, that Yorkshire probably wasn't the best location for an astronomical telescope. So the Crossley telescope was put up for sale, no takers, so eventually negotiations were entered into that Crossley would donate it to Lick Observatory, provided that Lick could organise for the relocation, including the enclosure, the dome there. So in 1895 the Crossley telescope arrived on Mount Hamilton, and it was one of the first reflecting telescopes, very new technology at the time, using a silvered mirror, and it was responsible for the first photograph of an astronomical source fainter than the naked eye. And when it first arrived, it was a very flimsy telescope. If your listeners get the chance to look on the internet at some point and see how the Crossley telescope appears now, it looks like a battleship gun. But when it first arrived, it was very novel, and it was a very open structure with these kind of trusses like modern telescopes would be today. It was way ahead of its time. But when it first arrived, it was described by the man who was assigned to get it working as a pile of junk. And abandoned for some few years, until a director of Lick Observatory, James Keeler, took it on as a pet project. And it was James Keeler who used it for photography, and also one of the early deployments of spectroscopy, the new science of spectroscopy. And it was James Keeler who took his photographs of deep sky objects and started to notice that the more he photographed deep sky objects, he saw more spiral nebulae and deep sky objects in the distance and in the background of his photographs. And he noticed that he became aware that as he looked away from the plane of the Milky Way galaxy, he saw more deep sky objects as well. So he was moving towards a cosmological idea sometime in advance of Hubble's confirmation of the extragalactic nature of Lord Ross's spiral nebulae.
The galaxies were called nebulae because we didn't realise that they were outside of our own galaxy.
Absolutely. So Keeler was very instrumental in moving our ideas forward towards our new standard model of cosmology. And there are advocates here on Mount Hamilton who would argue that had James Keeler not had an untimely death at the age of 36, he probably would have stumbled across Hubble's discoveries before Hubble himself had. So that's the Crossley telescope. Back away from the main building and go down the ridge a little bit, we have a 22-inch reflecting telescope, which was purchased sometime in the 1970s, I believe, which was the largest amateur-built telescope in the world. We also have a now empty enclosure on the opposite side of the road called the Crocodome, or the Crocodome, which has had various instruments in it throughout the years, including, I think, solar eclipse and solar study lenses, things like that. But the most recent has been what we call the Vulcan camera, which tested the technology for the current Kepler satellite that is in orbit detecting all these exoplanets. Moving away from the Crocodome, we then come up to the latest installation on the mountain that was installed over the past few years and being commissioned right now, which is something called the Automated Planet Finder, or the APF. And you can see the change in technology just by the enclosure. It's a very compact telescope. It rather looks like the enclosure looks like a golf ball on a pillar almost. And that's the most modern telescope on the mountain, and that's purely dedicated to the detection of extrasolar planets. So the belief is that when that goes into automatic operation later this year, hopefully, we'll be picking up about 1,000 exoplanets a year, which is comparable with Kepler.
I was going to say, so this is using adaptive optics? No,
this is using a radial velocity technique. There's a very dedicated spectrograph built on the back end of that telescope, on one of the Naismith platforms, which will measure the deviations of spectral lines from stars, and those deviations are caused by the orbits of companion planets.
As they go around the star, the Doppler effect will cause a redshift and a blue shift of the spectral lines.
Yes. The important thing is that in order to get very good sensitive measurements, you need a very stable spectrograph to do that. Very stable equipment, because what you do not want is the spectrograph to be flexing and bending on the back end of the telescope as you steer it around the sky. because that will also cause some deviation in your spectral signatures, which can be confusing. So the APF is a kind of joint project that has developed over time, led by people like Jeff Marcy and Steve Vogt, who we'll discuss a little bit later in the conversation. So you move away from the APF, the next dome in line is the Lick astrograph, which was deployed to take simultaneous photographs in two different photographic plates, 20 years apart of the whole northern sky. And that was basically a proper motion survey, or a transient survey, looking for changes in those two epochs. The astrograph is still in there and it's still operational, but we have not made it robotic or modernised it at all, and it's likely to be moved to an education centre at some point off the mountain.
All right. Okay.
Moving down from the astrograph in my mind, we then pass one of the most important instruments at any observatory, but also one of the smallest, which is a conditions monitor. We call it the DIM, it's called the DIMM, Differential Image Motion Monitor, which helps us quantify the seeing here at Lick Observatory, the conditions of the atmosphere, the seeing and transparency. And that's becoming critical now, especially in the era of remote or service observations, where the astronomer is not here to monitor the conditions themselves for their data, and they need all these data inputs to let them know that they are acquiring data of the sufficient constraints to meet their scientific objectives. So that's basically a small Meade or Celestron telescope on an automated platform.
And that's just pointing at a bright star in the sky and measuring the current seeing conditions. Yeah, and over time it will oscillate and it will go to different elevations and so on to measure the atmospheric transmission as well, how thick the atmosphere is and the effect it's having on the observations of the night, which you can then correct out in your observations. Oh, right. Just behind the DIM telescope, we then have the largest telescope on the mountain, dating from the late 1950s and early 1960s, the Shane telescope. And that's a 3 metre or 120 inch telescope, which also reveals its vintage and its heritage, because that is also an equatorially mounted telescope. Most of the modern telescopes now, like the APF for example, will be an Altaz telescope because we have the computers to control them. But the era in which the Shane telescope was built dates from the 60s and so on, and they didn't have the computing power, so it was mounted on an equatorial mount. It's actually a sister telescope of the Palomar 200 inch, because when they were building the Palomar telescope, they were unsure whether they were able to build a piece of glass that size at Corning in New York, and they basically worked their way up in scale. They would do a test blank on 80 inches, then a test blank on 100 inches, and then a test blank on 120. And it came to the knowledge of Donald P. Shane, the director of the telescope, that there was a 120 inch test blank lying over from the construction of the Palomar telescope, and he acquired that blank and built a telescope around it. And it's quite curious because the telescope is actually a very long telescope. The tube is very long because the original mirror was only a blank test. It could not be shaped into a very deep parabola, so they had to have the parabola shaped into a very shallow curve or shallow bowl, which meant that the secondary mirror and the focus of the telescope had to be constructed inside a very long tube. Yes. And when you get a chance to see that, it becomes evident that this is relatively, by today's standards, the 3 metre telescope is in an incredibly huge dome to accommodate this large telescope support structure. Donald P. Shane, who the telescope is named after, became director of the telescope right after the end of World War II, because as a stellar astrophysicist, he knew a lot about nuclear explosions, and he was seconded to the Manhattan Project and became Robert Oppenheimer's right-hand man at Los Alamos during the construction of the atomic weapons program in the United States. He was a very popular lecturer at Berkeley prior to that, and then he was seconded, and then after his war effort he came back and became director of Lick. Excellent. So that's the Shane telescope, and inside the Shane telescope we have an additional slightly smaller telescope, something like a 26 inch, which is almost a parasitic tube bolted to the inside of the enclosure, and that's called the Coudet
auxiliary telescope, and that sends a beam of light from a siderostat outside the building, a flat mirror outside the building, and that accommodates that beam of light going into this tube, which has the small curved parabola, and it sends it down to the coude room underneath the main telescope itself. So we can simultaneously observe with two different instruments, one on board the telescope and one in the coude room, down there in the basement of the Cheyne. So the Cheyne has two telescopes inside it, and that's important. The Cheyne telescope is very important historically as well, because it was responsible for the discovery of more exoplanets than anywhere else on Earth. And 70% of the first few hundred exoplanets were discovered here on Lick Observatory using the facilities inside that enclosure. The first solar type the first exoplanet around a solar type star was confirmed here by Jeff Marcy and Deborah Fisher and Paul Butler, working with the facilities there, because at the time the Hamilton spectrograph, which is another huge gravitationally stable spectrograph in the basement of the building there, that was one of the few high resolution spectrographs available to detect these motions in the spectral lines caused by the exoplanets orbiting their parent stars. So the Hamilton spectrograph and the Cheyne telescope are very important in the discovery of exoplanets. Also, the Cheyne telescope is significant because we have an adaptive optics system deployed using a laser guide star facility on that telescope, because here at Lick, unfortunately, the seeing is not comparable with other modern locations such as Hawaii, Antarctica and the deserts of Chile. So we lose out somewhat on the quality of the seeing. So we have technology which is a whole separate discussion, using lasers and so on, where we project a laser into the night sky up to 90 miles up, or 90 kilometres up, and that creates an artificial star in the sky which we can monitor and then correct the surface of a deformable mirror to take out the atmospheric turbulence and therefore correct our images and effectively remove the seeing completely, or remove the atmosphere from above the telescope completely. So we're basically putting that telescope into space. And the adaptive optics system and the laser was the first used at the Cheyne telescope. It was the first deployment of that technology anywhere for astronomical use. I think the military had it working a few years prior to that. But again, that was in the late 70s and early 80s that occurred. And the Lick, or the University of California Observatories, became a world centre for that technology. Moving on behind the Cheyne telescope, we have another telescope, a relatively new addition to the mountain as well, only in the past 10 years or so, which sits high up on a small peak called Kepler Peak, which is the Katzmann Automatic Imaging Telescope, or KAIT, K-A-I-T. And that is another dedicated telescope, small aperture reflecting telescope, which is dedicated to monitoring galaxy clusters looking for new supernovae. And that's looking again, going back to a cosmological perspective, looking at the expansion of the universe and trying to increase our statistics and our understanding of the supernovae that we are using as our standard candles across the universe to measure not only the expansion but this proposed acceleration and the dark energy that may be driving it.
So they're looking for type 1a supernova.
Or looking for supernova and then characterising them thereafter with follow-up on other telescopes. But that's an imaging telescope, so you would be characterising them with spectroscopy on follow-up. Once you've detected your new supernova, you can monitor them. So just going back, I mentioned one thing I overlooked was talking about the Hamilton spectrograph, this gravity-stable spectrograph used for the exoplanet detections. That was constructed by Steve Vogt, who's a California astronomer who is now involved in getting the APF, the Automatic Planet Finder, up and running. And many of those exoplanet detections were detected by Jeff Marcy, Paul Butler and Deborah Fisher, who are constant, still repeat observers here at Lick Observatory, and they are also involved in the APF project as well.
All right, well, thank you very much for your time today, Paul. I mean, it's been absolutely marvellous coming up here and sitting in the control room for such a historic telescope. And so thank you very much for talking to us today, and have a good day.
You're very welcome, in regards to the UK.
Without the help of John Schur and Sandra Masika, this wouldn't have been possible, so I would just like to say an extra special thanks to both of them for putting me in touch with the people at the Lick Observatory. I must say, if you get the chance, go and visit. They have a wonderful visitor centre there. You get shown round the Great Refractor, and James Lick is buried. Anyway, if you get the chance, make sure you go up there. Thank you to everybody for listening. Thank you to Dr. Paul Lynam, Sandra Masika, John Schur, and everybody else in the AFM team.